Hello everyone. In this video we're just going to have a quick introduction to the idea of memory caching. Before we do, these are some useful numbers that you should know going forward. These will be very handy for you when we're doing calculations about caching. So it's good to have a firm grasp of at least, let's say, the first 10 powers or so of 2, just so that you can easily calculate without having to use a calculator every time one of these comes up. Anyway, let's have a look at storage. Now, we've been working a lot with registers. We know that they only store bytes. They take less than a nanosecond to access, but they are very, very expensive, so we can only have so many of them. Now, the next stage of memory is something called cache or SRAM memory. Now, this tends to be megabytes that you have in your machine. For example, my laptop that I'm filming this on has about a 6 megabyte cache on a reasonably good CPU. This is very quick to access, about 1 nanosecond, and is about £500 per gigabyte. Now, it's a very expensive piece of memory, so there tends to be not much of it, but it is incredibly fast. Some of you likely have better processors than mine that have more cache memory. Generally, if you're looking at a CPU, that's a good thing to consider as something that's going to help it perform a little bit better. Now, the next thing we have is main memory. This is a DRAM or dynamic RAM. Now, the difference between SRAM and DRAM is that SRAM is static RAM, which does not need to be refreshed by an electronic pulse to keep something in memory, whereas dynamic RAM does. Now, dynamic RAM, sometimes just called RAM, it needs to be refreshed periodically to keep the memory, or to keep what is stored there in memory. So what this means is the processor might have to wait for the refreshing to take place before it can access the information stored there, and as such it's a little bit slower. Now, it's less expensive. It's about £10 per gigabyte. I think this machine has about 8 gigs of RAM, which isn't massive. Quite a lot of people have 16 RAM, some people have 32 gigabytes of RAM, 64 gigabytes of RAM. 8 gigabytes of RAM might be the reason why I can't record lecture videos. But you can see that just taking the step from cache memory to main memory, the time to access is about 50 times higher, which is obviously quite a lot, especially if you're really trying to tune a machine to the best possible performance you can get. Now, below that, there's solid state drives. I think my machine has a solid state drive. It's 512 gigabytes, but you can get terabytes and terabytes of that stuff. And it's quite quick to access as well for your storage memory. It's relatively expensive. I mean, it's about 5 times or 6 times more expensive than hard disk space, but it is about 100 times faster, so it can help your machine feel a bit snappier. So just some general advice if you ever wind up buying a laptop in the near future. Hard disks tend to be quite a bit slower. However, they are much cheaper, and you can get a lot more storage there by spending much less. And then, of course, you have network storage or OneDrive, stuff like that. The memory storage there is almost unlimited. You get as much as you pay for, and it takes about a second to access. So it's a fair bit slower than the ones above. And then, back in the good old days, we had tape, which you can get a ridiculous amount of. It takes ages to access, but is insanely cheap. Now, you might be noticing a pattern here, which is the faster it is, the less of it there is. And the faster it is, the more expensive it also is. So, accessing main memory, or your DRAM, is quite slow compared to the instruction rate. I mean, something that could take less than a nanosecond up to going more than 50 times slower. It's not ideal. So, accessing the disk is even slower still. So really, what we want to do, if we want to optimize at a low level, then we would want to make sure we could use cache. Now, what is cache? Well, when the CPU tries to get some access to some data, what it does is it just asks for an address. It's not aware of memory, it just asks for an address, and it has to go out to the address, find that location, and bring back the data stored there. Now, this happens over and over and over and over again, where we just go and ask for an address, get the data back eventually, but this is very, very slow. This takes about 50 to 100 instruction cycles to go through this, and so obviously we would want to find a way to optimize this and make it a bit quicker. Now, what we can do is introduce cache. Now, if we have a cache memory which is closer to the CPU and faster to respond, then what we could do is the CPU just asks for an address. It doesn't know anything about cache or memory, it just asks for an address, and if it's in the cache, it gets retrieved back immediately. Now, this can take 1 instruction cycle, so you can do this insanely quickly. But if you have an address that's not in the cache, then the CPU can, it can still be fetched from main memory and found, brought back to the cache, and then returned. So the CPU doesn't know about this cache or main memory, just asks for an address and it expects some data back. That's about all it does. Okay, so this is going to be another important idea, the principle of locality. So we have two ideas of locality. We have temporal, which is that recently accessed addresses will be needed again soon. So if you read something, you might write to that memory location again. If you're using a variable, you might update its value. We also have spatial locality, which is that addresses near to the current addresses will be needed soon. And you've seen this in practice, like when you have an array, then you're likely to go from one element to the next. So if you take the whole array out, you might save yourself some time. The same with local variables. If you put a bunch of them into registers or whatever into memory, then you would want to get them all out probably in a reasonably small amount of time. Same for stack frames. If you put something on a stack, you're likely to pop off of the stack and get it back soon. And for instructions, but we're not going to go into that in too much detail. So temporal locality implies that caching is a good idea because we'll be needing these soon. Spatial locality implies that we should load the neighbours of the needed addresses into the cache at the same time. So we don't just take one value, we take everything around it. And let's see what that looks like. So say we look for this red address, and we have a cache which has 2 blocks in it. We find that the address isn't there, so we go into memory to see where it is. And not only do we return the value when we've found it, we take the entire block. So we take everything around it, and we move that to the cache. Then we can just find the value from the cache and give that back to the CPU. And then when it comes time to find another address, we might find that that's in the cache and we can give it back in one instruction cycle because of this principle of locality. So data near to data just accessed will be in the cache, and this is a key way to speed up the processes of a CPU. So this is it for our introduction. I hope you found this useful. If you have any questions, please do let me know. Thanks.